We're going to switch gears a little bit and we're going to talk about solubility product. So we're still dealing with equilibrium in solution, but now we're looking at how soluble things are. So when we're talking about the solubility product, it is still the equilibrium constant. We're looking at dissociation reactions. So remember, when things become soluble, we put them into solution, they break apart into ions, and we're looking at those dissociation reactions. And so when we write our equilibrium constant expression, it is products over reactants, but because our reactants are always solid, our solubility product is just the ions, just the products. And we represent this as KSP, the equilibrium constant for the solubility product. There's lots of different solubility constants, and this helps us to determine how soluble or insoluble different solution or different compounds are in solution. These are some constants for insoluble solids. Now, solubility, remember, is how much stuff or how much solute we can get to dissolve in a solution, and we do have to keep in mind temperature because we can increase solubility by increasing the temperature. And the molar solubility is where we look at how many moles of the solute will dissolve into a liter of solution. Okay, and this is at the saturation point. Okay, so how much we can get before it starts forming that precipitate. Now, molar solubility is related to KSP, but we can't always look just at the KSP values to know how soluble or insoluble something is. We really do need to look at the molar solubilities because it depends on how many ions our solid breaks into to help us decide on the solubility. So the only way that we can compare KSP values is if we get the same number of ions in solution when it dissolves. So instead of looking at KSP values, a more useful value to look at is the molar solubilities. So let's try an example where we're going to calculate the molar solubilities. And so we want to look at our dissociation reaction. So in this case, we're looking at lead chloride. And this is a solid. We're adding it into a solution. And when we talk about things being soluble or insoluble, it really is a continuum. So even though it's insoluble, a little tiny bit will still dissolve. And so this would be our dissociation reaction. And so if we're writing our KSP, our solubility constant, it's going to be the lead ion times the chloride ion squared because of our stoichiometry, right? So we have 2 as a superscript because we have 2 Cl minuses. Now if we look at our ice table, so our initial change in equilibrium, We're starting with 0 when we add it to solution. And we tend to, instead of using X for molar solubility, we tend to use S. So our change is going to be plus S for the lead. For the chloride, it's going to be plus 2S. So because of that coefficient for the chloride. And so at equilibrium, we're going to get S and 2S. Now when we write our KSP, it's going to be S times 2S squared, which is going to be equal to 2 squared is 4 times S raised to the second is squared times S is cubed. So we end up with 4S cubed for our value. So if we want to figure out what S is, we are going to have to take our KSP. We have to divide by 4 to get rid of the 4, and we have to take the cubic root. And so if you don't know how to take the cubic root on your calculator, you may want to look at the instructions so that you can figure out how to do the cubic root. So the cubic root, we're going to plug in our KSP for lead chloride, lead 2 chloride. And so in this case, our molar solubility is going to be 1.43 times 10 to the negative 2 molar would be our molar solubility. All right, here's a practice problem for you to try. Pause the video, see if you can come up with the answer for this problem. So we're looking at lead bromide. So our dissociation reaction is going to be similar to our example. We've got 1 lead ion and 2 bromide ions. Again, I am terrible at putting states on things. Should be aqueous for each. Our KSP is going to be the lead ion times the bromide ion squared. So if we set up our ice table, remember we're not including the solid because it's not included in our equilibrium constant expression. Ice. Okay, so now that we get here, it says that our molar solubility is 1.05 times 10 to the minus 2. So we are trying to calculate the KSP. So that means that our S value is going to be 1.05. So at equilibrium, we know our lead is 1.05 times 10 to the negative 2. How about our bromide? What is our concentration of bromide going to be? Well, if lead is 1.05, bromide is 2 times that amount. So it's just 2S. I'll write this in here so you know where I came up with those values. So 2 times the molar solubility. So now if we want to look at our KSP or figure out our KSP, it is going to be the lead times the bromide squared. Now we've already accounted for that 2 times in our number here, so that's why we don't have the 2 in front of the bromide. So we're going to plug our numbers in. And so our KSP 4.63 times 10 to the negative 6 would be our KSP. So now we can compare this KSP to things that dissociate in the same way. So if we wanted to look at this compared to our lead chloride because they dissociate the same way, we can compare the KSP values. We also could compare the molar solubilities to see which is more or less soluble.